Hello everyone and welcome back. My name is Mr. Koval, and in this video I'm going to be talking about reaction rates. So first I want to talk about an analogy that I'm going to compare cars to the kinetics of reactions. So let's look at this table that I have here. Let me step on this side. Where are we looking at? So we can either look at what's happening with a car, or we can look at what's happening in a reaction involving reactants and products. So here, when we're looking at a car, we're looking at how fast the car is going, right? And here the units are miles per hour. So if we're measuring the rate at which the car is moving or going over a certain amount of distance in a certain amount of time, we're looking at miles per hour. And so to calculate that, you would look at the change in the difference over the change in time. Now, of course, this is not the instantaneous speed of the car. This would be the average speed over a particular distance and time. You would have to use calculus, or take the derivatives of the curve or the function of the change in rate, and then you would have to use again derivatives or calculus to do that. I'm not going to get into derivatives in this video, maybe at a later video, but here to start with, we can talk about at least the average speed of a car. And so to find the average speed of the car, the equation would be the change in the distance over the change in the time that you're covering that distance. And then this would give you the speed of the car. Now for kinetics, we're looking at the speed of a reaction. And so there we're looking at the change in molarity over time in seconds. So we're looking at the units of molarity over seconds, or capital M over S. And so as I said here, again, we're looking at the average change over time. So this is going to be the change in the concentration in molarity over the change in time that this change in concentration occurs. So this will give us the average change in the concentration of, say, a product or reactant over time. And again, this will give us the speed of the reaction over the average speed of the reaction over time. So if we think about what's happening with the reactants products, during the reaction, we're using up our reactants. And so that means that over time, we're going to see a decrease in the number of reactant molecules. And so as those molecules decrease, we should see a negative rate, right? Why? Because the change in the number of molecules is decreasing, so the rate is negative. When we're during the same reaction, we're making products. And so there we're going to see an increase in the molecules of products, and that's going to give us a positive rate of change. So the production of products, because we're increasing the amount of products over time, that's going to be a positive rate of change. And since we're losing reactants, that's going to give us a negative rate of change. But the rate of change in all of these should be the same for the reaction, although the rate of change of the concentration of products and reactants is going to depend on the stoichiometric relationships between the two. So I'll get to that in just a moment. So with this graph here, you can see that I have 2 moles of NO2, or 2 molecules of NO2 gas, is then going to break down into 2 molecules of NO and 1 molecule of oxygen. So here we have a decomposition reaction. And so we can look at the function of the concentration over time. So here, this is our, let me label this. So this here is concentration of NO2 over time. The green is concentration of NO2. The red is going to be the concentration of oxygen over time. And then the blue is the concentration of NO over time. So here, labeling our graphs. And so here you can see we start with, we start with a certain amount of NO2 up here, and we start with zero product. So at the beginning of the reaction, all we have is reactant, and we have zero product. So as time goes on, once the reaction starts, the number of NO2 molecules goes down. The concentration goes down as the amount of products, the concentration of products goes up. So NO is increasing, O2 is increasing as NO2 is decreasing. And we could look at the rate, right? If we did the derivative, we could, or the instantaneous rate of change, we could do our tangent function and do all that. And we could calculate rise over run and all that stuff. But here you could see the rate is changing over time. But here it is a negative rate of change, and for both of these, it's a positive rate of change. The other thing I want to point out is you can see at any one moment, it's not drawn to scale, but if you draw a line at any time, this is not drawn to scale, but what you should see is that the amount of oxygen produced should be half the amount of NO. Since, again, we're producing twice as much NO as we are oxygen, so at any given time, the amount of NO you see should be double the amount of O2. It's not quite double, but it should be. It's not drawn to scale, so you'll have to just deal with my artistic abilities. But that's what you should see here. So what you can see here is that you have these stoichiometric amounts. So for the amount of oxygen that's created in an amount of time, you're actually doubling the amount of concentration of NO at the same time, and you're losing twice as much NO2. So there's a 2-to-1 ratio here. So when you're trying to figure out the rate of the reaction, if you don't take into consideration the stoichiometric amounts here for each of the species, then you're going to get different rates of the reaction, right? So if I look at the rate of the reaction according to NO, and I know I'm getting twice as much NO produced as O2, my reaction might be considered twice as fast as that of O2, which doesn't make any sense because it's one reaction. So when we're trying to figure out the rate of the reaction according to the various species, we want to do that in such a way that we're going to get the same reaction rate regardless of which species we use to calculate that rate, right? So looking at here, if it's the amount of concentration, the change in concentration over time, well, the concentration of NO doubles, is twice as fast. That change in concentration is twice as fast as oxygen. So if I use NO, if I use this, and I don't take into consideration the stoichiometric amount, then when I calculate the rate of the reaction according to NO, then as opposed to, or in contradistinction or in juxtaposition to the rate of change with regard to O2, then I'm going to get a reaction rate that's twice as fast when I use NO versus O2. So how can I avoid that? Well, I need to take into account the stoichiometric amounts, the coefficients in the equation. Well, what do I do? Well, let's look here. So one, I can measure the disappearance of reactants, right? I can use that to measure the reaction rate. I can also use the appearance of products, right? I can use that to measure the reaction rate. If I do that, I need to take in consideration the stoichiometric proportionality of the various substances. So again, what I mean by that is the fact that I have a 2 here, a 2 here, and a 1 there. So I'm losing double the amount of NO2 that compared to the amount of O2 I'm creating, and I'm creating twice as much NO compared to NO the O2 that I'm creating. So we have to take into consideration the coefficients. And so we need to, for example, we're making twice as much NO as O2. So how do I do that? Well, I take in consideration the coefficients. And so in order to get the same reaction rate with respect to each of these species, what I do is I take the coefficient and I take the reciprocal of that. I multiply the reciprocal of the coefficient by the reaction rate according to that species. So, which makes sense because if I'm going to compare the reaction rate of O2 to NO, and I know I'm making twice as much NO as O2, then the rate of change with respect to O is going to be half that of NO. So I take half of that. So then they're equal, right? So the change in the concentration of O2 over time is going to be equal to 1/2 the change in the concentration of NO over the same time. So that means so that's making them equal. Notice I have a positive here and I have a positive here. The positive means I have a positive change in concentration. I'm creating more, I'm producing more of the substance over time. So I'm producing oxygen and NO over time. And then here it's equal to negative 1/2 of the change in NO2 over time, the change in time. And again, it's 1/2 because my coefficient here is 2. So it's a negative because here I'm decreasing in the amount of O2. So the change in concentration is negative. I'm losing particles of N2, so it's negative. So this is going to be a negative change that's equal to the positive change in O2. And so if I use this, if I use the coefficients, if I take the reciprocal of the coefficients and multiply that by the change in the concentration of that species over time, then I will be able to calculate the reaction rate with regard to each of these species and come out with the same reaction rate. So if I look at the reaction, if I find the change in concentration of O2 over time, or the concentration of ONO over time multiplied by 1/2, or the concentration of NO2 over time multiplied by negative 1/2, then whatever concentration I use, I can get the same reaction rate. So let me go on and talk about average rates of change with respect to concentrations. Okay, let's talk about average rate. So, what is an average rate? So, an average rate is basically what I said before is where you take the concentration of a substance over time. So, you measure the final minus initial over a certain time period. This rate is not always going to be constant. The reason for that is mainly because as the reaction goes, you're losing you're losing reactant. And remember, according to collision theory, you need particles to collide with each other in order to react, and only some of those are going to be have efficient energy. They're going to have effective collisions. And so if the concentration goes down, then of course the reaction rate is going to slow down. So the rate is not going to be constant over time. You can start off fast and then slow down, or you start slow and you speed up, but it's not going to be constant. Sometimes it is sufficient to just get an average rate. So you calculate the average rate over a certain time period, and then that's usually not usually, but that's sometimes good enough for whatever purposes that you want to use it for. So the average rate is going to be calculated this way. So you're going to find the change in the concentration of whatever substance or species you're interested in over a certain time period. And so again, when you do a change, it's going to be final minus initial. So you measure what the final concentration is at a particular time, and then what the initial concentration of that time was and then it's going to be divided by the final time minus the initial. So the change in time here. So it's going to be the change in the concentration divided by the change in the time of that reaction measurement. Okay, so here's an example. So in an experiment, the concentration of substance D was measured at different times. So here's the data. So at different times, the concentration of D is measured. So at time 0, the concentration was 0.500. 3.0, the concentration is 0.370. And then at 7 seconds, it's the concentration is 0.290. Now, notice from the table something here. At the beginning of the reaction, you start at 0.500 molar. That's the concentration that you start with of D. Then, as time goes on, what do you notice about the concentration of D? It's going down. So that should indicate what D is. Is D a reactant or is it a product? What do you think? If you said a reactant, you would be correct. Well, why is it a reactant? It's because the concentration is decreasing, which is what you would expect for a reactant over time. If the reactant is becoming product, then you should lose the reactant and gain product. So you should see a decrease in the concentration of a reactant over time. And that's what we see here. So we can infer that this must be a reactant. And then when you calculate the reaction rate, you'll see that as well. So we have two things. A, determine the average rate between seconds 0.0 and 7.0. And also B, determine the average rate between 3.0 and 7.0 seconds. So let's do A first. So we're going to take the concentrations. We're going to find the change in the concentration over the change in time for D. So we take our data. We're looking at 0 and 7 seconds. So at 0 seconds, the concentration is 0.500 molar, and at 7 seconds, it's 0.290 molar. So again, it's going to be final minus initial. So we take our final, which is 0.290, and we're going to subtract our initial, which is 0.500, and we're going to do the same for time. So our final time was 7 seconds, 7.0 seconds, and we're going to subtract the initial time, which was 0.0 seconds. And when we do the math, we get negative 0.030 molar per second. So that is the rate of change for substance D. And you'll notice it's negative. So again, that indicates what? So the question is D a reactant or product? We said it was a reactant because the rate is negative. It's decreasing. So we get a negative 0.030 molar per second. So we're losing this amount of concentration per second. So what about B? So B, we want to do the same calculation, but this time between 3.0 and 7.0 seconds. So we take 3 and 7. So the final concentration again is 0.290. So now we're going to take that and subtract the initial, which is 0.370. Subtract that, and then divide it by the change in time. So the final time again is 7.0 seconds. And this time we're going to subtract 3.0 seconds as our initial time. And then we calculate that and we get negative 0.020 molar per second. So in this case, we're calculating a rate of a decrease in the concentration of D by 0.020 molar per second. And you'll notice here that depending on what interval that we choose, we get a different reaction rate. And so therefore, we can see that the rate is not constant over time. So the rate of a reaction will change over time, And that is why using an average rate is not always the most helpful thing to do. A lot of times we want to find the instantaneous rate of change, which I will talk about in another video. So I hope this video was very helpful. If you enjoyed this video, you learned a lot from this video. If this video helped you in any way, then please like, share, subscribe my videos. Hit that like button right over there. Make sure you subscribe to my channel. Hit that notification button. And when you do, make sure you click all so you can be notified by all videos I put out. And finally, put a comment down in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. Thanks for joining me. Have a great day.